Hello everyone and welcome to this video in which we will learn more about time complexity of a computer program. Let's get started. Let us first consider a hypothetical machine with the following characteristics. First, it has a single processor. It carries sequential execution. It takes 1 unit of time for arithmetical and logical operations, and 1 unit of time for assignment and return statement. Now, let us take some very simple examples and try to figure out the rate of growth of algorithms in this hypothetical machine. Let's say that we have to find a program to find sum of two numbers x and y. This function just returns the sum of two numbers x and y. Now, if we run this particular function on our defined hypothetical machine, it will take 1 unit of time for this return statement and 1 unit of time for the arithmetic operator. So, the total time taken will be 1 plus 1, that is equal to 2, which is a constant. So, irrespective of the input, we will get constant running time for this function. Let's take another example. So, we have this function which finds the sum of numbers in an array A of size n. We initialize a sum variable to 0, and we have this for loop which runs from 0 to n, and inside the for loop we add the array elements to some variable. Finally, we return the total sum. Before analyzing the time taken, let me add line numbers to this program. And now, let's find out the cost and number of times each line execute. The first line execute once as it has a single assignment statement. Also, since for assignment only 1 unit of time is taken, the cost will be 1. Next is this for loop. The second line which has this for loop will execute n plus 1 times. This extra 1 is for the false condition, and let's say that this for loop will have cost 2, that is 1 for assignment and 1 for incrementing. The third line will take two number of operations, that is 1 for assignment and 1 for the arithmetic operator. This will execute n number of times. And the fourth line will execute once and it will have cost 1 for the return statement. So now let's find out the total time. The total time will be 1 plus 2 into n plus 1 plus 2n plus 1, which comes out to be 4n plus 4. We can replace these constants with c and c dash. So this is a linear running algorithm. Let me summarize the running time of the previous examples. The time taken for the first function, which was just for adding two numbers, was constant, which I am denoting by c. The time taken for adding the numbers in an array is cn plus c dash. And similarly, if we try to find out sum of two-dimensional array, we will get a quadratic function. Let's compare them on a graph. This is the input size and this is the time taken. The first is for this constant, which is obviously a straight line. The next is for finding the sum of array, which is a linear graph. And this is the graph for the quadratic function. Obviously, the quadratic function will grow at a much faster rate compared to the linear function. We often generalize this. For example, big O of n square will define the set of all functions of the form an square plus bn plus c. For the linear functions of this type, we generally use big O of n. And for constant functions, we have big O of 1. A general rule while finding the big O complexity is finding out the fastest growing term and ignoring the constant values. As you can see, n square grows at a much faster rate than n and constant. So we have ignored this whole term and just taken n square as the complexity. Similarly, we have ignored the constant and taken n as the complexity. This big O is the asymptotic notation that we have talked of in the previous video. In the next video, we will dive deeper into the asymptotic notation and discuss other notations as well. That's all for this video. Thank you for watching.